Hello everyone, myself Professor Tushar Gujrati from SND College of Engineering, Yevla. Today we'll study the tuning for PID controllers. So tuning is required while controlling different applications. We need to adjust values of P, I and D controllers, and then we get our actual output controlled. Okay. So the PID controller tuning involves selection of the controller parameters for optimum performance. This is known as controller tuning. So we select control parameters for optimal performance. So first of all, we need to understand PID controllers. So PID controllers are everywhere due to its simplicity and excellent performance, if not optimal performance in many applications. PID controllers are used in more than 95% of closed loop industrial processes. It can be tuned by operators without extensive background in controls, unlike many other modern controllers. So here we can tune the parameters. So in this case, the equation, the transfer function is shown in the box. Kp into bracket 1 plus 1 upon Ti into S plus 1 Td into S. So this is the transfer function of the system. So tuning a PID controller. System model is required for techniques use we have studied. Root locus, Bode plots, okay. System models may be determined using system identification techniques such as measuring output for an impulse or step input. Traditional control design methods are less appropriate if the system is unknown. Most PID controllers are tuned on site due to machine and process variations. The theoretical calculations for an initial setting of PID parameters can be bypassed using a few tuning rules. So what is written here? There are some techniques are available for measuring output. Okay. So traditional methods are very less available, and these PID controllers can be tuned on site only. We have to go on site and then we have to control. We have to tune these PID controls on site. Okay. Now, how do the PID parameters affect the system dynamics? There are four major characteristics of closed loop step response. These systems we have already studied: rise time, overshoot, settling time, and steady state error. These are all characteristics. These affect PID parameters. So rise time is nothing but it is the time it takes for the plant output to rise beyond 90% of the desired level for the first time. Okay, this is the rise time. What is overshoot? How much the peak level is higher than the steady state normalized against the steady state. So the whatever the peak is there, maximum peak in the output, that is called as overshoot. Settling time is nothing but the time it takes for the system to convert it to steady state. Okay, so this settling time is called as settling time, means time taken to settle down. And what is steady state error? The difference between the steady state output and the desired output. The difference between steady state output and desired output is called as steady state error. So how do the PID parameters affect system dynamics? The effects of increasing each of the control parameters Kp, Ki and Kd can be summarized as. So suppose there are three parameters Kp, Ki and Kd. If these parameters increases, so there is some effect on system. Okay. So rise time, overshoot, settling time, steady state error. So these all gets changed. So here in this table, NT means no definite trend. That is minor changes are there. So you check in this diagram, rise time gets decreased in case of Kp, Ki, and overshoot gets increased in case of Kp and Ki. Okay, so this is the difference. So in Ki, steady state error gets eliminated. Okay, but settling time increases. In case of Kd, overshoot decreases, settling time decreases. So these are some parameters, or this summary you should understand first of all. So how do we use the table? Typical steps are available for designing a PID controller. First step is determine what characteristics of the system needs to be improved. Okay, this you determine first of all. Then use Kp to decrease the rise time. Okay, Kp decreases rise time, that's why you use Kp. Then use Kd to reduce the overshoot and settling time. Okay, and then use Ki to eliminate the steady state error. So like this you combine all the three parameters. So what is written, this works in many cases, but what should be good starting point? What if the first parameters we choose are totally crappy? Can we find a good set of initial parameters easily and quickly? So these are the questions. Okay, so we are going to set the parameters kp, kd and ki. Okay, so the question is, can we set these parameters easily and quickly? Is it possible? So there are some methods are available for setting these parameters. So method is the Ziegler-Nicholas tuning rule to the rescue. So this is the rule, Ziegler-Nicholas tuning rule. So Ziegler-Nicholas conducted numerous experiments and proposed rules for determining values of Kp, Ki and Kd based on transient step response of a plant. So these scientists have done many experiments and then he proposed a method for setting values of Kp, Ki and Kd. So they proposed more than one methods, but we'll limit ourselves to what's known as the first method of Ziegler-Nicholas in this tutorial. It applies to the plants with neither integrators nor dominant complex conjugate poles whose unit step response resembles an S-shaped curve with no curve should. This S-shaped curve is called as the reaction curve. Okay, we'll try to understand these statements with the help of rules. Okay. So Ziegler-Nicholas tuning first method, S-shaped step input response curve. Okay, this is the first method. The S-shaped reaction curve can be characterized by two constants. One is delay time L and one is time constant T, which are determined by drawing a tangent line at the inflection point of the curve and finding the intersections of the tangent line with the time axis and the steady state level line. Okay, so it is here, there is one curve is available, steady state curve like this. Okay, so to this curve we have to draw one tangent over here at the inflection point. Okay, and this tangent interacts on the x-axis. Okay, so here this distance is called as L, that is delay time, and this distance is called as T, it is called as time constant T. So this is, we have to understand like this. So L is delay time and T is time constant. So now Ziegler-Nicholas tuning rule based on step response of the plant, first method. So there are different types of controllers, Kp, Ti and Td, or Ki and Kd. So for P type we need to understand the formula, that is T upon L. This is the formula. For Ti we should take infinity, and for Td we should take 0. If we want to use proportional controller, then we have to use this formula. Okay, if we want to use PI controller, then values should be taken like this: 0.9 into T upon L, and Ti is L upon 0.3. And if we use PID controller, then you have to use these formulas. Okay, by putting values of L and T, we will get the values of Kp, Ti and Td very easily, and from this we can tune the controller very easily. Okay, these values gives us some very fast and quick tuning of PID controller. So there is one more method, Ziegler-Nicholas tuning second method. So it starts with closed loop system with a proportional controller. Begin with low value of gain, that is Kp. We have to begin with low value of Kp. Potential of this method to go unstable or cause damage. So this method can go for unstable and damaged part. So now next, begin with low or zero value of Kp. Increase until a steady state oscillations occur. We have to increase this value of Kp until steady state oscillations occur. And note this gain as Kcr. We are going to assume this as Kcr. Next, this is the gain estimator chart. So here we have to measure Kcr and Pcr from the diagram. This is the diagram. In this case, Pcr is nothing but the distance between two peaks. Okay, this is Pcr. And Kcr is nothing but gain of this Kcr. So we have to put these values in this table, and from this table we will get the values of Kp, Ti and Td for different type of controllers. So the Ziegler-Nicholas tuning method to determine an initial or estimated set of working PID parameters for an unknown system. So we get parameters, initial and estimated set of working PID parameters, usually included with industrial processes controller and motor controllers as a part of the setup utilities. So usually included with industrial process controller and motor controllers. And some controllers have additional auto tune routines. So they have additional auto tune routines. They get tuned automatically. So these parameters will typically give you a response with an overshoot on the order of 25% with a good settling time. So these parameters will typically give you a response with an overshoot on the order of 25% with a good settling time. There will be overshoot will be present, but settling time will be also good. We may then start fine tuning the controller using the basic rules that relate each parameters to the response characteristic as noted earlier. So after this, we should go for fine tuning with some basic rules. Okay, we have to change the values of Kp, Ki, Kd very slowly, very finely. We'll get the control very proper. So now we'll get summary. Two things to take away from this review of Ziegler-Nicholas tuning. We get relationship between Kp, Ki and Kd and important response characteristics, of which these three are most useful. That is, use of Kp decreases rise time, use of Kd reduces overshoot and settling time, and use of Ki eliminates steady state error. So these three very important parameters we understand. And the second point, the Ziegler-Nicholas tuning rule, that is reaction curve method for good initial estimation of parameters. So this method gives us good initial estimation of parameters. Okay, so these are the summary points from this video. So thank you so much all of you for watching this video. So in this video we understood the Ziegler-Nicholas method, that is reaction method for PID tuning.